Welcome to today's panel discussion on syntactic foams, an update on research and industry applications. The Syntactic and Composite Foams conference was scheduled for 2020, but it could not take place due to the pandemic, and many other conferences have been canceled this year. So we thought to create a series of virtual events to catch up with the leaders in syntactic foam area. We want to acknowledge US aid funding to make some of these events possible. So today we are launching a series of 4 events. Each panel discussion will have a different focus within the theme of syntactic foams research and applications. And each panel will cover one geographical location because time difference is just too much between Australia, India, Europe, and the US. So we decided to have 4 different panels to cover these. We hope that information that emerges from these panels can guide some of the future research efforts in syntactic foams and make the research relevant to the needs of industry. So today we are fortunate to have 3 eminent panelists with us. They need no introduction to the syntactic foam community. So I want to keep their introduction brief from my side. Professor Orbulov is a full professor in the Department of Material Science and Engineering at Budapest University of Technology and Economics. He received his Doctor of Science degree in 2018 from Hungarian Academy of Sciences and PhD in 2009 from Budapest University of Technology and Economics. Dr. Orbulov's main research interest is the development of metal metric syntactic foams and related problems. Dr. Orbulov is the leader in composite metal foams research group. Dr. Gary Glad is founder and chair of the ECI conference series on syntactic and composite foams. He's an adjunct associate professor of material science and engineering at the University of Alabama at Birmingham. He's founder of the X-Link 3D, a startup company. He has worked in syntactic foams R&D for 20 plus years at National Labs Industry and University. His most recent work is in material extrusion 3D printing, the design of high glass transition temperature epoxy-based syntactic printing inks. Mr. Noel Tessier is one of the founders and technical directors at CMT Materials and Engineering Syntactic Systems. He has a BS in Chemical Engineering from Northeastern University and MS in Plastics Engineering from UMass Lowell. His work experience for the last 30 plus years has been developing and commercializing syntactic foam products. And some of the commercially developed syntactic foams that he's been involved with include specialty tooling materials, buoyancy products, sandwich core materials, insulation, ballistics, energy absorption material, and the list goes on and on. So now I'm going to hand over the floor to them. They can present a brief introduction about their recent activities and syntactic foams related work. Attendees can ask questions using question and answer utilities, which Gary Mack and I would be monitoring during the panel discussion. And we'll take some questions as we go. So I'll request Dr. Orbulov to give his presentation first and introduce us with the research that his group has been conducting recently. Thank you.
Thank you so much. Hello, everybody. Good morning or good afternoon, wherever you are. So I will try to share my presentation. Can you see this?
Yes.
Thanks. So let me introduce myself and thank you for the introduction. My name is Imre Orbulov. I am from Budapest, Hungary, from the Budapest University of Technology and Economics and the Department of Material Science and Engineering. I have 2 slides only, so I will be quite short. First of all, our location, it's Hungary in Central Europe, bordered by Slovakia, Romania, Slovenia, Croatia, Austria, and Ukraine, and Serbia. We have a quite nice capital called Budapest. As you can see here, it's a bird view for the heart of our city. And in the top right corner, it's the main building of my university. And right down is the bottom right is the good old department building of my department. Our research group was founded in 2018. I am the group leader currently, and we have 6 current members. First of all, Chilla Wiener, she's a PhD associate professor. You can check the pictures here. Dora Károly, she is a teaching assistant, sorry. Attila Slancsink and Alexandra Kemény are PhD students of mine. And Borbára Leveles and Domonkos Kincses are MSc and BSc students. So our group is quite small, but the guys inside are talented, and we all talking about and working about metal matrix syntactic foams only. We never did polymer matrix syntactic foams, so we are focusing on metal matrix syntactic foams only. I have to emphasize this because there are many questions will be in this panel discussion, and I will always highlight the metal matrix syntactic foams point of view. We have a web page and a list of publications. I will type the URL in the chat function, so every attendees can check it out. Thank you so much. That was all. Thank you.
Thank you. Dr. Gladys? You are on mute. We can't hear you now.
Okay, how about now?
Yes, we can hear you.
Okay, great. So let's see, I'm sharing my screen. That's right. You can see my screen?
Yes.
Okay, great. So this is sort of what I'm up to recently. While we're talking about syntactic foams, I wanted to highlight the LinkedIn group so that you can stay in touch. If you're already not part of that group, Syntactic and Composite Foams community, please join, and you can stay up to date. Nikhil mentioned the Syntactic Foam Conference, Syntactic and Composite Foam Conference that was canceled this year, scheduled for 2022 at this point, but this group will keep you up to date with the latest on that conference and everything going on in syntactic foams, so please join. In that nice introduction Nikhil gave, I am adjunct faculty at the University of Alabama, Birmingham. I do curriculum development, developing MS program in quality and manufacturing engineering, and I teach this coming semester. I teach a course on statistics and quality. And below that, you can see my book. And in fact, I just got an email today, and I downloaded the very first version, the electronic version of it. So it's hot off the press. So this is the first day of it. So it's an exciting day for me. Top right, I'm secretary of the ECI conference committee. So I start conferences, start different types of conferences. And as Nikhil alluded to, I started the Syntactic and Composite Foams Conference back in 2004, believe it or not, guys. I think Nikhil and Noel have been part of that from the start. And then just recently, this last year, we had our first innovative materials for additive manufacturing conference. And I recently started a startup company called X-Link 3D, and this is sort of a spin-off from work that I was doing that I am still doing on a CRADA with Oak Ridge National Lab in the manufacturing demonstrations facility, where we're looking at launching thermoset materials for 3D printing in direct ink write technology. It's a direct ink write technology. And, at this point, we were able to print a syntactic foam that was 80 pounds, and we can get down to resolutions of, 1 millimeter to a half millimeter at times. There's trade-offs on that, obviously, but that's sort of what I'm up to and where I'm coming from. So with that, I'll end.
Thank you very much. Noel, would you like to go next? We're not able to hear you. We cannot hear you, Noel. Yeah, your sound is not coming through.
Can you hear me now?
Yes, we can.
Sorry about that. So, as you said, I've been working on syntactic foams for a long time. They've been a material type and product class that fits me very well. I love the complexity of syntactic foams and the ability to engineer and manufacture them to meet customers' needs. I'll give you a little background that I started as a materials engineer in Army Mechanics and Materials Research Center. We had 350 scientists and engineers at the facility, and I worked in the composites development division. So I've learned all about fibrous composites and processes to make them, and I was exposed to scientists that really developed analytical techniques to characterize those composite materials. And I really feel that characterization is an extremely important thing on the materials that go into a syntactic foam. So upon leaving AMRAC, though, I became technical director at W.R. Grace Emerson & Cummings division. I found the technology there at Emerson & Cummings was based mainly on empirically derived products. And I was able to then bring the characterization learning that I had at the Army Materials and Mechanics Center and bring that and the composites knowledge to syntactic foams. And with that, I think we were able to improve the performance and consistency of syntactic foams. Another benefit of working at Emerson & Cummings is we actually made our own microspheres as well, and I was able to understand the property of microspheres to the performance relationship in syntactic foams. With this new understanding of the microspheres, I was able to develop new, improved syntactic foams from that. So syntactic foams have been really exciting for me. We're constantly learning about how to engineer and process syntactic foams and finding new applications. I've had a chance to test syntactic foams for energy absorption from ship speeds of about 15 knots to automotive speeds of 35 miles per hour, to NASCAR speeds of about 200 miles per hour, to ballistic speeds of 2,000 feet per second, and then finally to explosive rates. Syntactic foams absorb energy over this whole range of rates in almost consistent values. Examination of the failure modes at different rates showed differences, and this lent evidence to the ability to design them for these types of applications. So in the middle of this, though, the company that I worked for changed ownership, and the focus was diverted away from these kinds of applications. At this point, I left Emerson & Cummings, and after the transition year, started CMT Materials with Tony Colagio, Tom Murray, and myself, and that's how we got CMT, Colagio, Murray, and Tessier. As a startup syntactic foam business, we decided to develop syntactic foams for thermoform tooling. We found once that we understood the customer's needs, we were able to engineer better syntactic foams for the industry. It was the most exciting work yet. It is great to be able to engineer a syntactic foam of better performance and then seeing the use of this material impact the whole industry. Now being in business for 21 years, we continue to find new applications for syntactic foams. I find there's always something to learn about syntactic foams and where they may fit in the marketplace. The syntactic foam conferences have been excellent for me. It reminds me of working at AMRAC, where scientists and researchers have new discoveries and techniques that can give knowledge to the syntactic foam community. That's it. Thank you.
Thank you very much. So since you all come from a little bit different backgrounds, like Emre is from metal matrix composites, and Noel and Gary have mostly focused on polymer matrix composites, one thing that remains common is the particles. And Noel mentioned a little bit about his experience with different types of particles and their development. So I wanted to start the discussion with a question about the particles, that What is the future in this area? Are we looking for new types of particles, particles of new materials, new shapes, new functionalities, and what could be beneficial? So Noel, would you like to start first? Yeah.
I would, yeah. The properties of the hollow particles that are used in syntactic foams are so critical and dominate the performance. I think in syntactic foams, you're always pushing to get the optimum level of those hollow particles into the product, and thereby that's why they dominate the performance, because you're not balancing the properties of the hollow sphere or the hollow particle with the matrix to get to the optimum performance of that microstructure. You're always trying to optimize the packing of the hollow particles. And so measuring the properties of those particles is really important. One of the questions that I have for the group, and one of the things that I look for, is that are there newer materials that could bring specific strength and stiffness to these hollow particles, bring higher temperature performance, and the main thing is, are there materials that could reduce the brittle failure mode that we see in syntactic foams? Have any of you been aware of any new materials that could handle that?
Well, I'd like to chime in a little bit there. I like to define hollow particles by sizes, right? I think on the micro level, I think it's fair to say there's been a stagnation on the particle types that are available from a production standpoint. I think glass has been around since Emerson and Cummings in the early 1950s, right? And then 3M came along in the 60s, and Potter fits in there somewhere with Ohio in their process. And then I think there's a lot of exciting work going on in the nano range right now, hollow nano structures. I think there's a lot of interesting work going on in there, and I'd like to see a lot of that transition in. And then there's the macros, right? The millimeter size and larger, which there are startups now with a lot of different functionalities and different materials that they go into, from reinforced concrete to, just name it. There's companies out there now. So that's how I like to think about it. But, addressing Noel specifically, I think there is some sort of stagnation, and they're sort of stuck on traditional ways of processing hollow spheres on the micro scale.
Yep, I agree.
On my side, regarding metal matrix syntactic foams, the main problem is the production, because most of the production methods are using molten metal in liquid state, and therefore this temperature can harm the spheres, of course, and therefore we are almost always using ceramic spheres or metallic ones, but they are a different group. And in the case of ceramic hollow spheres or hollow particles or porous particles, it doesn't matter. The main question is the wetting between the metal and the material of the particle. So if anybody can develop particles, porous particles with metallic coatings, for example, that will be a huge help on us. And if we are considering aluminum matrix, that is the most commonly metal matrix syntactic foams, for example, coatings like copper will be perfect, because the wetting between copper and aluminum is perfect, and copper can be can have a strengthening effect on the matrix material as well. So that will be a huge leap in the case of metal matrix syntactic foams, I think.
Imre, coating technologies are available, and I think you have published some papers in coating these hollow particles. What are the real challenges that need to be addressed at the industrial level for this coating technology?
I mean, the mass production is the most important, so the price should be reduced. When I'm buying hollow spheres and materials, that the invoice is quite high. So the price should be decreased to have better possibilities to commercialize the foams themselves.
I've seen publications where people have tried to fill these hollow particles with certain gases or liquids, even magnetic liquids. So do you see any applications or even futuristic applications where novel particles like this might be useful?
It's a hard question. I never thought about that, but maybe there can be some applications. Again, I have to refer back to the production method. So, for example, if you have an overpressurized sphere in liquid state aluminum, that can be a problem. So there are safety questions as well.
Okay. Any other opinions from Gary or Noel? Anything that these filled hollow particles can provide in terms of advantages in applications?
Yeah, I guess the only thing that I have run across is, and I forget the exact chemical, but people were asking for higher dielectric properties, and you know, look for gases. I forget the specific gas, but you know, usually this is just a diffusion process. You get a glass microballoon, and it's diffusing the gas through the shell of the sphere, and this takes temperature and time, and so this is usually quite costly. You could get creative in the blowing agent at times to sort of tailor what you want inside that gas, and look for reaction products, gaseous reaction products in the blowing agent. But other than that, those are the only two ways I would know about doing.
Okay, yeah, I see. Sorry, go ahead.
No, I was finished. Thank you.
Okay, I see two questions which are related here. So the first question is, Gary, you commented that glass microspheres have been stagnated. So what are the desired new attributes in the particles? What is needed and what is desired?
Well, one of the things that I've thought about is if you could have a similar specific strength and stiffness from another material. And for instance, if you could have a metal microsphere in the same size of a glass microsphere, for instance, aluminum, which would have similar properties to glass, could you make a hollow aluminum sphere that then wouldn't have as brittle a failure mode potentially as glass, and therefore bring syntactic foams out of the fracture mechanics failure modes that limit us into the applications that we have? Do you see any possibilities of that ever happening?
So there's another question about the same thing that you mentioned, Noel. Are these metallic hollow spheres available for any of the metals? Have you seen examples commercially?
I haven't, no.
No?
No.
Okay, so I think that may be one thing on the list that we can identify.
Yeah. Also, is there a way to couple the spheres better, like Imre had talked about? You know, coupling is the real big thing, and how do you get the matrix and hollow spheres or hollow particles to work together in a composite structure? And so are there coupling systems that could be used to prevent that brittle failure mode as well in hollow glass microsphere type syntactics or in ceramic microspheres?
So these particles are available in large ranges now, from 10 microns to several millimeters. Now you can commercially acquire these particles, and now nanoscale are also available. Do you see any challenges in distributing these particles evenly when you do the manufacturing of syntactic foams?
They create rheology problems, obviously, and therefore how do you get the packing levels up to where it's a significant property that you want out of the final product? And so, you know, particle packing and binaries and tertiary sphere diameters are really things that could be improved over time. There aren't really good ratios out there available in microsphere structures to get packing levels up. And that's an area nano microspheres or something like that could potentially help. And then sometimes we find in the applications that we have that we don't quite meet the property that we're trying to get with the syntactic foam. Everybody knows that they cost more money and everything, but we don't get quite to the lower thermal conductivity that we need, or the lower density that we need, or properties that syntactic foams bring to really make it worthwhile to pursue.
If anybody else wants to chime in.
Yeah, as far as the smaller you go on microballoons, you know, when you get down below 15 or so microns, micrometers, you get flowability problems. So not only is it a rheological problem in the mix of the thermoset, whatever you're using, if you try to feed this into an extruder or whatever, you'll get a lot of bridging, and it just doesn't work as well as, you know, the larger microballoons. But, you know, the smaller you go, the better specific strength properties you're going to get out of it. So, you know, that's another issue.
Okay. So I wanted to stay with you, Gary. You have a startup that's in 3D printing space. 3D printing has become really big. So what challenges and opportunities do you see in 3D printing of syntactic foams?
Yeah, thanks for that question. I think in general, right, there's a lot of opportunity in 3D printing. People lump 3D printing into just one big category when there's actually 7 different technologies or family of additive manufacturing techniques that comprise additive 3D printing when you say that generically. And so, you know, each one of these are new processing techniques, and they open up new design windows on materials development and materials design, or part design. So I think that's the exciting part about it. And the one exciting thing is, you know, Noel was just talking about how viscosity, rheology is a problem when you try to load too many microballoons in there. Where I'm working on direct inkwrite with thermosetting polymers, epoxy specifically, you want that higher viscosity. So, you know, what's typically a problem in traditional processing of syntactic foams has sort of just been turned upside down by this direct inkwrite technology. And, you know, let's load more. We want this viscosity higher so we can process, so we can build bigger. So that's sort of an eye-opening thing for me. And I'm just working on one specific type of material extrusion, one subcategory of those 7 technologies, and I think there's a lot of opportunities in those other ones for syntactic foam for researchers to explore. So, you know, it's been exciting so far. Noel has helped a lot in this new technology as well, partnered a little bit during this CRADA, and I think there's a lot of room for syntactic foam development in some of these other 6 technologies, as well as a lot of opportunity within the direct inkwrite field as well. And I think if you look for these negatives in traditional processing and try to turn them into a positive on the 3D printing side, that's where you're going to get a lot of benefit.
Mm-hmm. Yeah, I agree with you. And one thing that we noticed was it was always difficult to produce syntactic foam with less than 40% volume fraction of particles, because they will always settle. And with 3D printing now, you can print syntactic foam with only 10% or 20% particles in there. And as long as you can make a filament, or you can do the thermoplastics ones mixing on the go. So that's one possible thing that we have seen from our side. So thank you. So Imre, I had a question for you, that your work has been mostly focused on...
Sorry, but on 3D printing and metal matrix syntactic foams, I have never seen any metal matrix syntactic foams printed in 3D. So I think it's quite impossible, but 3D printing is a very good production method to produce particles with irregular shape, not spheres, but let's say ellipsoids or any kind of. Okay, it's extremely expensive, but if the properties can be set and developed, then it may worth a try. Thanks.
Yeah.
Sorry for.
No,
Yeah.
my question was along the same lines that you mentioned your work has been only focused on metal matrix syntactic forms. So if you would be able to comment on your relationship with polymer matrix syntactic forms in the way that what have you learned from there that has been useful for metal matrix syntactic forms, or from your work, what can polymer matrix community can take and benefit from?
It's easier to answer the first part. I think everything. So polymer matrix syntactic forms were the pioneers in this field, and we are trying to do the same with the metallic matrix. So the next step is graded foams and functionally graded foams and bimodal distribution of particles and so on, that was already developed. That were already developed in a polymeric case, but it's not so easy to do the same in metallic matrix because the production temperature is higher. It's more complicated to handle the materials and so on and so on. So we are trying to run after you and do the same in metal matrix syntactic foams as well.
So I see a question which I actually get quite often in email from people. What is the largest size syntactic foam block that is possible? And Noel can talk about industrial availability. Imre can talk about metal matrix. And Gary, maybe you can comment on how big you can 3D print a syntactic foam block. Please.
Well, for thermosets in what we do, I think, you know, if you just use hollow glass microspheres, the largest thing that you can make is maybe 2 foot by 2 foot by 2 foot or something like that. But if you add then the macrosphere type technology with hollow glass microspheres, I mean, you can make almost any size that you want to with that. It depends on your ability to flow materials and the volume of that mix into whatever mold or cavity or whatever you want to do. So there's a pretty unlimited size that you can make with macrofoam syntactic foams.
Imre?
Yes, in the case of metal matrix syntactic foams, it depends on the production technology as well. If you take the most simple stir casting method, I think it's almost unlimited or limited by the size of the furnace and the mold. Of course, there may be questions about the evenness of the distribution of the particles, but large sizes can be done by this way, I think. In my lab, we are using pressure infiltration. Liquid state pressure infiltration. The largest part we can produce in our furnace is let's say about 70 times 70 times 100 millimeters, so much smaller than the one mentioned by Noel. But again, it depends on the furnace. But in furnace technology, if you increase the size, then you have to increase the pressure and so on. So it's again getting more and more expensive.
Gary?
It was part of the CRADA that I mentioned at the opening of this with Oak Ridge National Labs Manufacturing Demonstration Facility. We are doing large-scale 3D printing. So the print bed on this is manufactured by a company called Magnum Venus Products, and that print volume is 16 feet by 8 feet by 3.5 feet tall. So we're really limited to that space, but that's a significant increase from what most people see in this extrusion technology, which are the desktop type 3D printers. And so far, the largest one, as I mentioned, we printed an 80-pound part, which is nowhere close to the maxing out that part bed size. So.
Okay, so I'll take one more question from the audience. What are the applications that you see coming up for syntactic foams, the commercial applications? especially in metal matrix syntactic foams, we haven't seen many applications. There are always potential applications. But if you are aware of places where they have been used, or maybe where it's low-hanging fruit, so that would be good to know.
That's correct. Yes, that's correct. So in my opinion, mathematic syntactic foams would be beneficial where density and temperature is important. But as they are quite expensive, so it's quite expensive. That's the main problem. And let's take an example. Let's take an example of an automotive factory doing cars for roads and so on. And if you tell them, okay, here is a metal matrix syntactic foams, it's lighter and so on. The first question is, how much does it cost? And if it's more expensive by 1 cent than a steel part, they will ignore it, whether it's lighter or something like that. So money is better only, I think.
Okay. Okay, and Noel and Gary, if you would like to comment on upcoming applications, things that we have not seen commonly in commercial domain yet. We always talk about buoyancy and thermal insulation, but apart from that, what else have you seen?
For me, I think in fire performance seems to be an area that really is exciting, and energy absorption would be areas. In fire performance, one of the nice things about, like for instance, hollow glass microspheres is that you have an inorganic volume that you've filled with that, surrounded by a polymer. And so if it's like a phenolic material, and so therefore you don't get distortion in that material as it comes in, as much distortion in a fire situation, and prevents stresses from actually focusing into other and concentrating into other areas that lead to the failure of the structure itself and allowing the fire to proceed otherwise. And then other new areas I think are really in the thermoplastic matrix syntactic foams and what can be done with those to really lighten structures and to maintain high mechanical performance.
Yeah. Gary, would you add anything to that?
Yeah, I just want to follow up on one of the comments there. You know, when you look for a one-to-one, when you have a part and say, I want to replace this with the syntactic foam, rarely will it ever win. And as referred to, it's always going to lose on price. So you always have to say, well, what does the old part do? And then what else do you want that new part to do? So, you know, it's usually a monofunctional part that you're trying to replace with a more expensive material. So you just have to keep piling on functionalities and then designing the syntactic foam from these additional functionalities and try to bring in as much as possible to the syntactic foam. And that's where I see syntactic foams winning in the long run. It's not a one-for-one replacement of an existing metal part just to lighten it up. It has to be that and something else. And then just to follow up on the fire prevention materials. I've worked on intumescent macrospheres that can be placed on the top of hydrocarbon storage tanks that can perform better and won't sink like floating roofs tend to do, and can live on top of these fuels and hydrocarbons for years and years and years, and be, and prevent full surface fires on these storage tanks, whether it's crude or whether it's some sort of refined product.
Mm-hmm. All right. So,
one application in energy absorption where we did really good with syntactic foam, and the alternative material was cement, did really good as well. And so, guess which one won that battle? Even if our performance was a little bit better, the customer didn't care because cement could do the job.
Mhm.
Like, and it was for a floating application, you know. It's like, but anyway.
So that comment was interesting, Gary, that price is always higher. But why is the price higher? Because we got 50% porosity inside. Hollow particles, glass ones are much cheaper than the matrix material. So on the basis of raw materials, you can create a product which costs like half. But I would guess then the labor cost is just too high for these materials to be competitive.
Yeah, I think Noel would be better suited for that, but for me, yeah, it would be the processing costs and the time to create a part.
One of the issues, I think, is syntactic foams haven't had a big enough volume need. In offshore oil buoyancy, I think it finally got there. And then people built plants that could actually get the labor costs out of it per unit volume of syntactic foam made. So we lack in manufacturing into the volumes of consumer products to get the labor costs out. We make most of the time batch products in syntactic foams, and you know, the labor in a batch process is really high. I think if we could ever find an application, and that's why, to me, energy absorption was a potential area. If we found a big enough application, we could develop manufacturing processes that would get that cost out.
Okay. So there's a very interesting question I see. It's about large scale structures. So in thermosetting resins, there is this exothermic reaction when you cure it. And creating large scale structure becomes a problem with that. The heat is trapped inside. And I'm aware of some large scale products companies tried where they self-ignited during the curing process. So are you aware of any methods or technologies that have been deployed to make it possible to cast large scale thermosetting structures?
So I guess I'll speak up on that. And
Sure.
Noel sort of alluded to this. You can put in macrospheres to lessen that exotherm. And then from a 3D printing standpoint, they have what we call sparse to solid infill. So you can just form sort of a web of material underneath, and when you get to critical surfaces, that's the only time you put solid material down. Otherwise, it's just this grid structure building up until that critical surface is needed on the part of the tool or whatever you're trying to build.
Mm-hmm. Noel, would you add anything to that?
Well, to me, it would be similar to what Gary said. I mean, you can constantly be increasing the volume as you let some of the reactivity out of the material and then make it in one step, but it would be multiple. For instance, pores would be pouring different mixes on. And we've done that in submarine applications where we've filled like the diameter of a submarine piece at multiple pores in one process, and been able to do that.
Okay.
Yeah, the nice thing about working with epoxies, especially the uncured epoxy, adheres well to cured epoxy, where thermoplastics don't do it as well. So you don't have to worry as much with epoxies. You can just do the pour on pour, like Noel alluded to, and build up the structure that way.
Yeah, there's a question right along that lines that what innovations do you see in the matrix materials that could help syntactic foams? Or do you want any research efforts in this area that can make life easier in syntactic foam community from the resin community coming in? Gary, maybe you can start with that, and you have the 3D printing with some unique needs for the resin properties themselves.
Yeah, absolutely. So exotherm is a big concern. So in general, what I'm trying to develop are latent cure systems, so that they don't have to cure or solidify on the part bed, and then you can take them into a curing oven or just take them offline off the part bed and cure them how you need to under more controlled situations. So, I don't, right now I'm focusing on epoxy, but I think there's big opportunity in this area in general for direct inkwrite materials. And if people have ideas, please talk to me about it, connect with me, and I'd be happy to talk about exactly how we process this, how we print it, and then how we post-process to get parts or tools or whatever you want. But that's a good question. There's definitely a need for. I muted myself, especially in these new 3D printing technologies.
Would you like to add anything, Noel?
Yeah, I can't think of anything as to that. I mean, we know there are exothermic reactions, and how do you get away from that? I mean, that would be materials. How could you create bonds without releasing energy?
If I could chime in here first, and I think the syntactic foam community watches the polymers and the matrix development community pretty closely, and when something new and exciting is out there in a production volume, I think the syntactic foam people are at their heels, seeing if it's going to work for a syntactic foam. That's just my general sense being around the community for a while.
Maybe conducting resins or carbon nanotube reinforced conducting resins or something like that might help in the exothermic reactions. Imre, yes. Do you see any scope for improvement in the alloys which are available specifically for the purpose of syntactic foams?
Yes, I think the situation is easier in the case of metal matrix syntactic foams because you can widely vary the properties of the matrix alloy by alloying, of course, by heat treatments, or even reinforcing it by ceramic particles that can be found in the, let's say, conventional, in the case of conventional metallic foams. So the same can be done in the metal matrix syntactic foams. To tell you the truth, we are working on it actually. So I think we will be able to publish some new results recently. So that's all.
I'll stay with you for another question. That these coated glass microballoons or coated hollow particles, do you coat them yourself, or are they commercially available as well?
No, I'm looking for them. I saw the chat. There are metal coated glass hollow spheres. I'm really interested in it because we try to coat the spheres, and of course, coating technology is a great thing, and it's let's say some of them is quite easy to do, but not in the case of a pack of hollow spheres. So coating is easy if the surface is homogeneous and let's say flat, but if you have a pack of hollow spheres, they are not conductive because they are ceramics. It's not so easy to make an even coating on the spheres themselves. So we developed a small scale device that we can apply zinc coating on the spheres, but it's not productive enough. So that's the problem here.
Okay. So one thing I heard from industry recently was the efforts to create syntactic foams for sub 6,000 meter depth. And there seem to be some unique challenges there with buoyancy that you need to have, and three-phase syntactic foams with entrapped porosity apart from hollow particles seem to be the way to go. So do you have any comments about these ultra deep water syntactic foams, their production or research or development?
The technology, excuse me, the technology I'm aware of is just, not just to use hollow glass spheres, so, and then to get this microstructure to be strong enough to handle the loads. So the new materials that are out there, I'm a little skeptical, but we'll see how they perform.
Mm-hmm. Anybody else would like to add anything? No? Okay, so I'll change the line of questions a little bit. Modeling and simulation studies have been conducted by a lot of researchers. And Noel, I think in your initial introduction, you focused a little bit about the lack of theory-driven approach and mostly empirical approach in some of the initial works that you had seen. So what are your thoughts about modeling and simulation studies, and how could they be beneficial to industrial applications?
Oh, I think they're really beneficial. Obviously, we did some work with you and Lorenzo Badella there, and to understand the performance of a syntactic foam. Once we use the correct properties of the materials and the packing factors that you get, and the modeler was able to do some really great work, I thought, and that really helped a lot. The other technique that I think, and modeling can help in the analysis of how stresses go through the microstructure and all of that in a way that can help us to define what's the initiator of failure in syntactic foams so that we can start to work on the right area of improving their performance. The final technique that we've been using more and more is design of experiments and understanding the relationships in a statistical way so that we can make better and better decisions about how to design that material.
Sounds good. Gary, would you like to add something about that?
I guess I'm not a modeler, so I'll just give an impression of what happened a few years back with the James Cameron Deep Sea Challenger. I noticed that, well, before this time, syntactic foams have never been used as a primary structural component, meaning if it fails, the whole thing goes down. And to me, the buoyancy before this just literally floated on the vehicle itself, right? There was no clamping, no anything. It just, and it was only exposed to hydrostructural, hydrodynamic forces, yeah, and hydrostatic forces. And it seems to me that there had to have been some modeling done there because it was literally the backbone of that vehicle, and there must have been more complex loads and forces on that as it went down. So I was heartened by the fact that it was used as a primary structural material in that, and was hoping that things would springboard from that to more critical components for syntactic foams.
Imre, what do you see as the need for modeling and simulations in metal matrix syntactic foams?
Yes, thank you for the question. Nowadays, my students are working on the complete modeling of the whole compressive curve of a metal matrix syntactic foam to implement it in a finite element method program in order to make modeling like crashing boxes and so on, where not only the critical load matters, but the energy absorption and so on. It's not so easy to do because in a compressive mode, you know that syntactic foams are compressible. So we are using a model that originally developed for powder metallurgy parts, and we are trying to do some modification to be applicable for metal matrix syntactic foams, but I can tell you the truth, it's not so easy. So we are fighting with that. My PhD student Attila Slanchik will use it in his PhD defense as well. So we are doing large efforts to solve this problem, at least for a few matrix particle combinations, because of course it depends on that, of course. Thanks.
Okay, so if you had in your wish list the top item for research community, because we have lots of students and professors joined on this call, what would be that item that they can address through their research? Anybody can start that. No, what's okay? Gary, go ahead, please.
Yeah, so just sort of, I didn't want to take Noel's thunder, but just, you know, the brittle nature of it and understanding failure. You know, and getting back to my comment as a primary structural component, we just don't understand fatigue. We don't understand failure mechanisms, and you know, they're brittle. We don't know when they're going to break, which is holding back a lot of applications for lightweight structure. So that's the one thing that I've always wished for, just an understanding of fatigue and failure mechanisms.
Yeah, yeah. One for me is that we don't really know the tensile and shear properties of syntactic foams at these depths. We measure those properties at ambient conditions, and yet we find failure modes when we go deep that shouldn't be happening based on those ambient conditions. And for me, I'd like to have some researcher or some laboratory be able to look at the shear strength under hydrostatic load. I think it's been done in the cement community for the building cement structures at the bottom of the ocean. But syntactic foams, we don't know what the tensile properties is once you put 5,000 psi of pressure on a material. And is there a way to do that? Is there a way to get a tensile strength at that? We see in the modeling that we've done, we've seen an increase in von Mises stresses of about 500 psi in a bonded assembly with different layers of stiffness of maybe fiberglass or adhesive or whatever, and even the density difference in the material. And yet when it goes to depth, it actually starts to failure with only a 500 increase. And yet we have tensile and shear strengths of 4,500 psi, and we're seeing a 500 psi increase failing these structures. Like when you build a structure to go to the bottom of the trench, how did they understand what the properties of that foam were really going to be when they get down there? So in the research community, if that could be measured somehow, I think that would help us a lot to understand how to prevent those failures.
Okay. We have only a couple of minutes left, so if you have any final comments, you can take a minute each. Can we start with you, Gary?
Yeah, sure. Just getting back to, you know, I want to sort of jump over to the metal matrix foams and maybe suggest how to make this through additive manufacturing. We did some powder processing on the polymer side of a BMI with glass microballoons with powder bed fusion, so a laser fusing layer by layer. And I think that would be an avenue that you could use for the metal matrix, because they do use metal powders in these powder bed processes, and you can mix in your ceramics with that as well and just do layer by layer with the powder bed fusion technique. So a crossover there that we might be able to help with.
Noel, would you like to go next?
Sure. One of the things that I really appreciate what you do, Nikhil, is actually get out the message on syntactic foams. A lot of the developments that we've had, really the designer understands that syntactic foams may be something that they could use. And so they would come to a syntactic foam manufacturer and give you the idea, right? And then now you have to modify that material system to meet whatever it is. So the more that we're able to get out that message that syntactic foams have these unique properties and what can be done with them, I think then that's a great thing. So thank you very much for that.
Thank you for your comment. Imre, any final comments?
I just would like to say thank you for inviting me for this panel talk. It was really interesting, I think, and I have learned a lot of things. Thank you so much.
Thank you very much. I wanted to thank all the panelists for taking time out and talking here today. And I also want to thank all the attendees. I can see the names of a lot of people who collaborate with us or who are well known in syntactic foam community. There are numerous questions that we have not been able to answer, but I hope that this panel discussion will start communication. And Gary's LinkedIn group on syntactic and composite foams, that can be a forum for us to continue this discussion there. So the next panel is planned for January 14th as per the US time. This will be, and let me share the screen one more time about that. Sorry, sharing screen here. Okay. So this panel on January 14th is going to be January 15th in Australia and India, and it's going to be late night on January 14th in the US. The registration is open now. I'm going to post it on the LinkedIn and also circulate with everybody who has registered for the current panel. Please feel free to send us emails. Gary Mack is the lead student organizer. I want to thank him for organizing this whole panel discussion, and feel free to register for the next panel. Hope to see you there. Thank you very much, everybody, and have a good day.
Thanks, Nikhil. Thanks, everyone.
Thank you. Bye-bye.